So the next section that we're going through is the periodic table. So for this, we started off with something that you guys learned in bio, so our Bohr diagrams. So remember, that's a way that we can represent the atom. We learned later on this isn't the most accurate or newest way, but it does help us for this unit. So in your Bohr diagram, your first energy level can hold, or your first ring can hold 2 electrons. Second one can hold 8 electrons. And then for what we're going to be doing for our Bohr diagrams, third one can also hold 8 electrons. So we're going to be using these diagrams to look at like how the size of the atom changes as you go across and down the periodic table. So for this, we're going to want to draw out Bohr diagrams. So lithium has 3, in its neutral state has 3 electrons. Beryllium has 4. And boron has 5. So to draw these out, we're going to have our nucleus in the middle. We're going to have our first ring, and then we'll have our second ring. So for lithium, since the first ring can hold 2, we're going to have 2 electrons in that first ring. And then we only have to get up to 3, so there'll be 1 in the third ring. For beryllium, we have our nucleus, we'll have a first ring, and then our second ring. So we're going to put 2 in the first ring, and then to get to 4, we're going to put 2 in the second ring. Boron, nucleus, first ring, second ring. So we're going to do 2 in the first ring, and we'll do 3 in the second ring. So to figure out the trend going across, we have to look at how much charge do those outer electrons feel from the nucleus. So since lithium is 3, that means it has 3 protons in our nucleus. So the nucleus gives us a +3 charge here. Beryllium, its nucleus would give us a +4 charge, and boron, its nucleus would give us a +5 charge. However, not all of that charge makes it to those outer electrons because these inner electrons are shielding some of that charge. So for each of these, we have 2 inner electrons. So 2 of the charge is getting shielded. So the outer ring only feels a +1 for lithium. Here, for beryllium, it only feels a +2 charge from the nucleus. And here, it only feels a +3 charge from the nucleus. So as we go across, the charge that the electrons in the outer ring feel from the nucleus increases. So since there's a greater charge from the nucleus, they're going to be more attracted to it, which makes your atom become smaller. So since this has a +3 charge, it's a greater charge, those electrons are going to be pulled in closer to the nucleus versus this +1 charge. So as we go across the periodic table, so as we go this way, your atomic size decreases. Now, we didn't actually have to go through this math. We could have just looked at how many electrons are in the outer ring. So here we only have 1 in the outer ring, so we only have 1 valence electron. Here we have 2, here we have 3. So that's another way that we could have figured out how much charge they're feeling. So that was the harder of the 2 trends. The next one is as you move down the periodic table. So we're going to do lithium, sodium, and potassium. So lithium has 3 electrons, sodium has 11. So here we're going to have to do our nucleus, our first ring, our second ring, and in the sense it's in the third row, well, it'll have a third ring. So we have to put 2 electrons in the first ring. Second ring can hold 8, so I'm going to put 8 in there. And now if we count right now, I'm up to 10. So I have to put 1 more electron in there, so I'm going to put 1 more electron in the third ring. So we can look, the outer electron, there's only 1 of them, so from the nucleus, this outer ring feels a +1 charge, which is the same as lithium, which makes sense because they're in the same group. Okay, next one is potassium. This one has 19 electrons and protons. It's in group 4, so I'm going to draw 4 rings. So my nucleus, my first ring, my second, my third, and then my fourth. So I'm going to put 2 electrons in my first ring, 8 in my second. So I'm up to 10 right now, so I'm going to do 8 in my third. And so I'm up to 18, so I'm going to do 1 in my fourth ring. So here, this again only feels a +1 charge from the nucleus. So as I move down the group, what I notice is that we have more and more rings. Those electrons are further out, those outer electrons are further out from the nucleus. So that means as you move down the group, your atomic size is increasing. So as I move down, atomic size increases. Okay, so next is our ionization energy. So your ionization energy is the amount of energy it takes to remove an outer shell electron. So energy required to remove an electron from the outer ring. So we have a trend going across and down the periodic table for this one. So as I go across, there is more charge from the nucleus on those outer electrons. So that means they're being held, there is a stronger pull between the nucleus and the outer electrons. So that means it's harder to remove them. So as I move across this way, I'm going to use IE for ionization energy. My ionization energy increases. So again, it's because we have more pull from the nucleus, so it's harder to remove those. As I move down, the electrons are further and further away from the nucleus. So think of like if you had 2 magnets really far apart. It's not as hard to remove them versus 2 magnets that are really close together. So since they're further apart, as you move down the periodic table, your ionization energy is going to decrease, because the distance between the nucleus and those outer electrons is greater, so it's easier to remove them. So ionization energy decreases. Okay. So the part of the periodic table that I didn't cover because it's in your notes, so if you pull out your periodic table notes, you can find it pretty easily, is the information about metals, nonmetals, and metalloids. So there you're going to want to know like some properties of them, what color they are on the periodic table, those types of things. So that you're going to look up on your own. I'm going to move on to the next unit, so that's electrons in the atom. So for electrons in the atom, we started off at the flame test lab and looked at color. So we knew as we went from red to purple, your amount of energy increased. So as I go from red to purple, energy increases. And then we looked at, if you guys remember, the house model. So the house model was like the rules of when you could fill which room. So the rules for filling, we always start on the first floor, or always start with 1s, and then you move to 2s when 1s is full. 2 electrons can fit in the s orbitals. 6 electrons can fit in the p orbitals, and then 10 electrons can fit in the d orbitals. If you remember, they fill each box of the orbital before doubling up. And then let's go through like the order of how these fill. So you start with the 1s, you then would go to the next lowest energy, so you're working your way upwards. So I'd go from 1s to 2s. The next lowest one is 2p, so I'd go to there. then comes 3s, then 3p, then 4s. There should be a 4 right there. Next, the next lowest one is 3d. So I'm going to come over here to 3d, then 4p, then 5s. So once we figured out that that's how they filled, we then wrote like the manager code. So let's say I was doing this for chlorine. So chlorine has 17 electrons. So I would start at 1s. I'd put one arrow up, one arrow down, because remember they always had to have opposite spins. Go to 2s, then go to 2p, so you fill each of the boxes first before you double them up. Then I'm going to go to 3s, go to 3p, I'm going to fill each of them first before I double up. And I'm also going to stop right here and count how many I've used. So I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I need to put 2 more in. So I'm going to go 16, 17. And then to write my manager code for this, I start going in the order that I filled. So I filled 1s first, and I put 2 electrons in there. I then went to 2s, and I put 2 electrons. Then 2p, I put 6. 3s, I put 2. 3p, I put 5. So that would be our code or electron configuration for fluorine. We then took this into our periodic table and looked at what it looks like on our periodic table. So for on our periodic table, we have these different orbitals actually show up as blocks on here. So here, we're going to take out helium from right there, and we're going to put it right there. So this is 2 blocks, or 2 elements wide, which is the same amount of elements that could fit in your s orbital. Over here, this was 6 elements wide, which is the same amount that could fit in your p orbital. And then here, this is 10 elements wide, which is which fits in the d orbital. So looking across, we can see the first one that you hit if you're moving down the periodic table is the s group. So right here, these first elements, helium is 1s. Lithium's group would be your like 2s. Over here, there isn't a first p block. So p doesn't start until the second level. So this will be 2p, where you have boron starting. And then we so 1s, 2p, and so d is going to start right here is going to be 3d. So this is where it gets a little interesting, because before 3d was 4s, and after 3d is 4p. So you can use the periodic table to fill out your manager code. You're going to start at the top, work your way across. Once you get to the end of a row, you're going to start the next row, work your way across, start the next row, work your way across until you hit that element. So this is the majority of what we did in electron configuration. So I would suggest to look over your notes a little bit, but this should be pretty much it for this unit.